So I'm going to simulate an AR model. Let's do AR2. In the base package in ARMA, there's something called ARMA sim. So you can simply use ARMA sim to generate a series. First argument is where you specify the model. So some list. So you would specify the AR part, then you would specify the MA part. Since this is an AR2 model, I don't want the AR part, sorry, MA part. So point eight. Let me ask you, what should the next coefficient be? I'll give you choices. 1.27, negative 2.56, 11.82, 0.29. Why, Emma? Should become absolutely summable. So let's do 0.29. Doesn't guarantee that we will have a stationary series of elements, but I think we will have one. Going to put n. N is the length of the series. Let's do 256 time points. So, or as you all know, it is a hopefully statistical programming language. So it has a built-in method for time series, a built-in object for time series. So you can use that easily for real-life applications. When we get to data, I'll show you that too. Okay, that should do. Okay, there we go. What does it say? Not stationary. Not stationary. Well, let me put minus 0.29. But so you observe something like this in practice, you may think, wow, that's some garbage result. Correct. It's just mess all over the place. How am I going to predict in the future? Seems like it's not seems like it's completely random, unlike linear regression, where you see a pattern, non-linear regression, see a pattern. Nothing here. Agree? So, to the naked eye, it doesn't seem like there is a pattern, but can we predict stuff using this series? Yes. If you can identify that this is an AR2 model. So, the next two steps over here, if you push it 4 steps, you can predict. One other thing, I'm going to do a case here for y under 4. If I run again, do you believe that I'd get the same series? No. because I need to have a seed. So let's put the seed up here.
What does ACO stand for again?
Autocorrelation function. Okay, this way when you run at home, see things look the same. Okay, let's say in practice you are observing some process, you end up seeing that series. As I mentioned a couple of lectures ago, the last time we did, the very first thing that one would do in time series is to look at the autocorrelation function. That tells you as to what order that you can use for the AR part, at least. MA part, not that easy. So, doing an AR2, forget this part, forget that you knew those values. All I have is the series. The next step is that autocorrelation function. Model identification when it comes to autoregressive models is just simply look at the ACF. It tells you, well, one, there, the maximum value that you can have is 1. At time 0, I have a value of 1, which means xt is correlated with xt itself. No lag. If I'm correlating with myself, total narcissist, everything is great about me, right? 100%. Perfect. So, easy way to remember. 1. As time goes along, it decreases. Those 2 peaks are above that blue dotted line. Yes? So, they indicate significant coefficients. Anything past that, useless. Good? So, I have a series that I observed. Forget about the simulation part. Observed. Next step, I get an ACF. I look at it, I see 2 peaks. I immediately conclude, okay, ARMA model is a good fit. And specifically, what order should I use to? Luckily, great thing about AR series, over here, the first value, it's about 0.6. Yes. And over here, it's 0.2. Yes. So if it is an AR1, whatever value you observe here in the graph will be the coefficient. So last time, I believe I did AR1, whatever you have here will be the coefficient. With AR2, not so easy. We have an algorithm, but once you have a series, you can immediately identify the number of coefficients you need. Good?
It's a random question, but what's the meaning of the second dotted line?
This one?
Yes.
So the upper and lower bounds, 95% confidence level. So upper bound, lower bound, anything that goes outside is not significant. So for instance, if I got another vertical bar right here that went out, then I would use AR3. But the moment something goes inside those blue lines, we will stop.
They go below the bottom one.
Yeah, it can't. But you follow this order starting from the first. The moment a particular lag value has a correlation that falls below the dotted line, you stop. It could be on the positive side, it could be on the negative side, doesn't matter. Okay, that's the AR part. Going to do the same. Only this guy, change it to MA. Change AR to MA, and let's see what happens. I'm going to retain the same coefficients. Maybe I'll change the color to good. But MA to series. What's the correlation function? Here, one of them here is going up, another one borderline. So I'm going to go for order 2. But is this an auto-regressive process? It is not. Not because I simulated an MA2. Auto-regressive processes are easy to identify because once you start at the initial value, rho equals 1, it will slowly decrease, monotonically decrease. But if things go back and forth, it's not AR. Here you've got that line going below, negative 0.2. There it is above, it's not AR. AR models consistently move in this direction. Again, that should make sense in a practical way. If you are regressing time points now to previous time points, you are looking at the same series. Things have to decrease over time in some way. Last case, we'll do ARMA 2.2. So I've got the AR part and MA part. Give it a different color. Eventually we'll get to the high parts in the ring. Stage. So the series this time is ARMA 2.2. You don't know, right? Model identification is not easy. You've got values going up there, values down there. So it could be just an MA model. It could be an ARMA model. But if someone asks you what are the chances that this is an AR model, I would say unlikely. I would lean more towards ARMA or MA. Could I be wrong? Sure. It happens. Reason being, just like a scatter plot that you use for linear regression, it is an initial impression. I observe this series right there, and then I compute an ACF. I see this. I'm making some initial inferences. If I look at something like this, I would either go toward NA or ARMA. Good?
Is the reason for that because it dips to the negative?
Yep.
Okay.
AR part, if it's a purely autoregressive model, it should go like this. And sooner it drops down on this side, that's fewer number of coefficients. Are we clear? Now toy around with different values over here. I'll take this split. And that will give you an idea of simulating ARMA models.